So in today's video, we are going to now take a look at these arithmetic and geometric patterns that we've been seeing and look at the applications, look at the real world applications to them. One of the big parts that we're going to look at is interest, but then we're also going to look just in general of growth and population or bacteria and some of those different pieces. So when we look at interest, there's two different types of interest, more so even three. So the two main types of interest would be arithmetic and geometric types of increases, so adding versus multiplying. So for simple interest, if I purchase something and I have to pay a set amount every year to cover that, and it was a percent of my increase, that would be what my interest would be. You can think about it as if you were working in a job and right when you signed up, you had two options. You had the ability to receive $1,000 every year increase because that was 10% of what you made. So you're going to get 10% of that initial amount for the rest of the time you work there. So every time you get the same increase, $1,000. Or you could choose to have compound interest, which means you get a percentage of increase upon what you're making each year. So say you get the first year you get $500 interest. So now it's whatever you're making before with that $500 interest, and now it's interest upon the interest, and then interest upon that interest, and interest upon that interest. So there's a constant multiplier that's in there. That's like that geometric pattern that we saw, and then your interest rate for that is as follows. So 1 plus r to the n times that initial amount that you put in there or that you were getting or whatever it is based on the story. And then the last one is that annual interest, but now it's being compounded a certain number of times a year. So instead of getting interest at the end of the year, so instead of getting that raise once a year, you get interest every month. You get interest every quarter. You could get interest every day. But it's still a set amount of interest over the entire year. But now what we're doing is we're breaking apart. Let's say we got a 12% raise. We're going to get 1% each month. So I'm going to get 1% of that in January. And then in February, I get 1% of that 12% because it's equal across the board. But now what happens is come December, I made interest on November's, which was making interest on October's, which was making interest. So you're making a little bit more. And this is our formula for that. We've got to break our rate into however many times it's compounding. So these are your interest rates formulas for each of the different situations. In your packets, they are not going to give you these formulas. What they are, however, going to give you is this formula, compound interest formula. It's just a little messier to work with. So they define what the values are. So future value is what it's going to be in the future. So it's whatever your present value, it's what you're starting with. And then the rate here, they have it as a percent, which is why they're dividing it by 100. Versus here, we just have what our rate is as a decimal. Oop, here it is. And then it's dividing it by k, which is the number of times it's compounding each year, and then to the k(n) power. So again, you're given this formula, but they're not going to give you these two. So make sure that you know your formulas there. Okay, so we're going to practice a few of these with interest, and then we're going to look at a population problem as well. So Sebastian took out a loan for a new car that cost him $35,000. The bank offered him 2.5% per annual simple interest for 5 years. So now it says simple interest. That's an important thing to see. So you're going to be only charged simple interest. So whatever you're charged the first time, you're charged the second and third and fourth time as well. So since the car costs $35,000 and the bank is going to charge him 2.5% simple interest for 5 years, we're going to use that simple interest formula. And more so, you don't have to really memorize the formulas, just think about what you're doing. So the amount that he's going to have, or repay, is based on how much he originally owed, so $35,000. Since he's owing more money, it's 1 plus. If it was depreciating or something along the lines, it'd be 1 minus. And then it's going to be the number of years based off of the percent. Now change that percent into a decimal. So that's what we're going to end up multiplying together. So 5 times 0.025, add 1 to that, again, because it's 1 plus it. So what they end up having to pay is 1 plus 0.125, because it ends up being 12.5% off of this original value when all is said and done. Add that to it, multiply, and we end up getting $39,375. So you could just find the interest rate if you didn't do the 1 plus. If you just multiplied the 35,000 by this, you'd just find out how much interest that he had to pay. In the next example, we have $5,000 being put into a savings account that pays 4% interest per annual, compounded monthly. So now this one is going to be, we're just doing a monthly piece, even though it was 4% every year. So now the amount that we have in there is based off of that $5,000. Since it's making money, it's 1 plus. Since I'm taking this 4% and splitting it up monthly, that decimal is 0.04, and I'm splitting it into 12 equal monthly payments. And then the number of times this is compounding. So this is going to compound for 4 years. But every year it compounds 12 times, which is why it's 12 times 4. So it's going to compound 48 times. So if I put this into my calculator, I end up getting 0.003 repeating. So I'm just going to keep everything in my calculator exact. Do not round anything until the very end. So therefore, if I type all of this into my calculator carefully, here's my recommendation. Do this first, then do +1, and then do second answer, caret 48, and then multiply it by 5,000. That's kind of the order that I would recommend doing this in. If that was the case, you would end up having $5,865.99. What I did is I rounded this correctly to cents. This is an exact value according to the story problem. So this is exact. This one as well was an exact value that we had. So there's no rounding going on with any of these problems yet. We're doing dollars and cents and we're making everything make sense, or it's exact. In the next one, she had a loan for $12,090 and she had to repay $16,000 in 2 years. What is the annual interest rate if the interest on the loan is compounded monthly? So again, we're compounding interest monthly, and I'm not telling you what the interest rate is. But what I'm telling you is in the end, she had to pay $16,000. She started with a loan of $12,090. 1 plus, because that money's going up, the interest rate, which we don't know, divided by 12, because that annual interest rate is going to be split up into 12 equal interest rates, not payments, rates. And then it was for 2 years, so it's going to be to the 12 times 2 power. So then I can go ahead and solve this. So I'll divide both sides by the 12,000. I'm not going to get nice numbers. So how I'm going to represent that, I'm going to put dot, dot, dot. That way you know I'm using the exact value in my calculator. And then this is 1 plus the rate over 12 to the 24th power. So now solving, I've got to get 24 over to the other side. So I'm going to 24th root this. So again, into my calculator, I'll do second answer, caret, parentheses, 1 divided by 24. And I get this ugly number. And then I'm going to subtract 1, multiply it by 12. R ends up being 0.1409, etc. So this is not an exact value. So since this is not an exact value, I have to round it. So therefore, I've got to go 3 decimal places. And it asked what the interest rate was. So therefore, it is 14.1%. Next one. Oliver's savings account now has a balance of $900. So that's what he has right now. The interest rate was 1.5% per year, compounded quarterly this time. How much did Oliver originally deposit 6 years ago if he has not withdrawn or deposited any money? So where does the 900 go in for? Does it sit all by itself on this side of the equal sign, or does it go over here? 900 is what he ends up having 6 years later. So this goes here. We don't know how much he started with. And then it's 1 plus the interest rate divided by, since it's quarterly, 4. It's in the bank for 6 years, and since it's quarterly, it's 6 times 4, or 4 times 6, either one works. And now I get to solve for this. So therefore, when I type this into my calculator, I get 900 equals x times all of this together is 1.093, etc. So divide both sides by that. Again, 900 divided by second enter. And I end up getting 22.68 is rounded to cents correctly. So again, I rounded to dollars and cents, which would be then an exact value. So the only one I didn't do an example with is if I'm just making an interest rate of 5% yearly, and that's it. Then instead of dividing by 4, it would just be plus your rate to the power. So that's what you really focused on algebra and algebra 2. Now that we're past that, now we're looking at compounding more often. So in this case, quarterly. Okay, so the last problem that we're going to work on is population. And this is going to be a little bit different than interest because we're usually looking at just the growth. And this is going to be a little closer tied to algebra 2 material, but now we're also going to look at the growth rate. And we're going to look at that piece a little bit more specifically. So in this case, it says, so for part A, find the net increase in the population of the city. So if I want my increase, so in 2015, I had 13.49 people. In 2016, 405,000 people moved in, while 331,000 people moved out. So the net increase of population in that year, so if this many people moved in, so it's a positive number, so I'm going to start with that one. And then this many people moved out, so I'm going to take them away. So therefore, my net increase, it's positive because more people came than left, is 74,000 people. For B, it asks for the population growth rate. So this is going to be new for you. The population growth rate is we're looking at how much did it grow compared to what the population was. So our growth was 74,000 people. The number of people that were there already was 13,491,000. So we just divide the two to get our rate. So for our rate, not C yet, sorry. So for my rate for this one, we end up having 0.00585. So we're going to round that 3 decimal places. Not 3 decimal places, sorry, 3 significant figures. So that's my rate. Sometimes they'll ask you for the percent growth. So if they want the percent growth, just move that decimal place in 2 spots. So 0.549% growth. Okay. Part C, assuming the rate continues the same, find a formula for the population. So the goal being we can find the population 15 years later. So this is very similar to what we were doing with geometric sequences. However, you have to start with this initial value. So initially I had all of these people. So 13,491,000 people times what my rate is. Since it's going up, it's 1 plus my interest rate, or my growth rate, so 1.00549 to the t. And one of the things that you need to do is define t. T is the number of years after, when did we start? 2015. And this is an equation, so we should have, let's do P for population. My population equals. Okay, and then part D, now we're going to estimate the population for Tokyo in 2025. So in 2025, how many years after? So that's where this comes in. How many years after 2015 is it? So it's 10 years later. So therefore, P equals 13,491,000 times 1.00549 to the 10th power. This value here, since I needed it later on, you need to have this value exact. So I know for our decimals along the way, we decimal approximated them. But you always go back to the exact value that you calculated up top here. So take that to the 10th, multiply it out, and you end up getting 14,249,168 people. So that's how you can use your formula that you created in C. And then it says, is that value reasonable? What did we just take a look at? People moving in and moving out. Does anything else affect population size? Births, deaths, those sorts of things as well. So is this reasonable? I mean, it might not be terribly off, but maybe there was something crazy that happened, or maybe Maybe the population is declining because the population is older and there's less babies being born. Like none of that is taken into consideration. So is this accurate or is this reasonable? I'd say technically no, it's not. But it shouldn't be too far off. Okay, so this is our work going through, just using some applications with it. You're going to do a few practice problems, and hopefully that'll help solidify, making the connections as well to what you did in Algebra and Algebra 2.